All right. Hi, everyone. Thank you for the introduction. Yeah, this is a joint work with my collaborators. First, co-author Bo and Mohammed and John. And so in this problem, we'll consider the storage-assisted energy procurement problem for a large-scale energy customer. Say that you're a data center or a university campus, and as a participant, uh, say you have energy demands that are revealed over time, and you can also meet these energy demands by purchasing from, let's say, a real-time market. And we also say these prices and demands are subject to uncertainty since these inputs are revealed over time. And so at time one, you receive price P1 and D1, and then so on and so forth over the time horizon. And in order to mitigate this uncertainty, the participant, say, also has access to on-site energy storage. This also makes the problem non-trivial, and the decision in each time set is to decide how much electricity you want to purchase from the market. And then in this manner allows the participant to buy electricity when prices are low, and then discharge from storage when prices are comparatively high. So in this particular example, say at time one, if the participant decided to purchase a quantity D1 plus D2, and then in the second time slot with a comparatively high price P2, it doesn't have to purchase at D2, it will just discharge that amount from storage. And so robust algorithms have already been developed for this problem, where they make really no assumptions about future inputs other than, say, the prices between an upper and lower bound. And we say these algorithms are robust in the sense that they have provable performance guarantees regardless of the actual evolution of prices. And then alternatively, in line with the rest of this session, you can realistically use extensive forecasting and prediction tools to make predictions about future inputs. And so now we say the participant can decide how much energy to purchase in each time slot and subsequently solve this problem based on their forecast. However, if the predictions are incorrect, the total cost may rise drastically. For example, say if an incorrect prediction determines that there will be a higher demand in the next slot, the algorithm may opt to unnecessarily stockpile electricity at a higher price. And then the majority of this work is we discuss a learning augmented algorithm, which basically does both simultaneously. And so our goal here is to still incorporate predictions about future inputs, but also provide performance guarantees regardless of the accuracy of these predictions. So just as a brief background, the framework we'll be considering is in online algorithms and online decision-making. And so here the inputs are revealed piece by piece, and the future inputs are unknown. And then we say the main performance metric here is called the competitive ratio. And so here we take the cost of an online algorithm and we divide it by the cost of an offline optimal algorithm, which actually knows all the future inputs in advance. And so then we take the max over all possible instances, max over I. And then since the online algorithm cannot do better than the offline optimal, this ratio will always be at least 1, and we want this to be the lower the better. And so actually for the storage-assisted energy procurement problem, this has already been solved, but it doesn't take into any consideration forecasting or predictions about inputs. And so that will be the main thrust of this work. And so just a brief overview. So learning augmented algorithm still receives the same sequence of inputs, but these can be augmented by predictions about these inputs. We basically consider it as these predictions as almost a black box, and it has some kind of unknown error epsilon. We don't actually know epsilon until the full input sequence is revealed. And so in this setting, the competitive ratio is now additionally a function of the prediction error epsilon. And so a slight modification to the metric metrics in this setting. The first is the consistency eta. So this is the competitive ratio when the prediction error is 0. And so we can call this consistent basically when we say the prediction is consistent with the ground truth. And so the best possible that we can do in this setting is one consistent, because here the online algorithm will match the offline algorithm. And then the second metric we consider here is robustness gamma, which is the competitive ratio for arbitrary prediction error. And so we say this is robust because it's robust to regardless of the accuracy of these predictions. So the best possible robustness will match the competitive ratio of an optimal online algorithm, which will ignore predictions. And so in summary, these two metrics will consider these two opposite settings of accurate and inaccurate predictions. And there is an inherent trade-off here. Since there are two metrics, we want to design something that is Pareto optimal. The existing algorithms leave something to be desired. They're usually lacking in one dimension compared to the other. Say, for example, the optimal worst case algorithm, it has a comparatively high consistency, whereas the pure prediction-based algorithm, if you solve the optimization problem directly on what the predictions give you, it will have a comparatively high robustness. And so what we want to do is design a learning augmented algorithm that will give the best possible consistency eta for a given level of robustness. And so in our contribution, we want to design a general class of Pareto optimal algorithms for what we call general online search problems. And then we can show that this will apply to the storage-assisted energy procurement problem. So just to give some background, the foundational problem that can be applied here is called the K-min search problem. And so the problem setup is pretty straightforward. So say that you want to purchase K units of an asset over a time horizon, and we know that the prices are just lower and upper bounded between L and U, which is a pretty general assumption. And so we say that over each time, in each time slot, you observe a price PT, and then you make an irreversible decision for the amount that you want to trade in each time slot XT, and then you will incur a corresponding cost XT times PT. And the goal here is to minimize the total cost summation of XT PT, and all you have to require is that the total sum of XT is K, so that you actually do buy the K units. And so in this talk, I'll just be focusing on the minimization problem, but our work also can apply this to the maximization problem if you are trying to sell items. So the general intuition for this problem is that you generally want to buy more units when prices are low and correspondingly buy less when prices are high. But the design challenge here is that if you wait too long for lower prices to arrive in the sequence, it may leave you with an undesirably high cost in the last moments of the time horizon, and you have to fulfill the obligation of buying K units. So this intuition for algorithm design can be formalized with an online threshold-based algorithm. So that here you will define K threshold values of phi sub I. And basically, you just need to follow the curve here to determine your buying decision whenever a price arrives. And so just to illustrate, say that you have an online arrival of a price P sub T, and you keep track of how much you've bought so far. So in this example, if the amount you've bought so far is 2, that's your current utilization. And then you set your buying decision based on the smallest threshold that is greater than PT. And you'll set that value, corresponding index of phi there, to be your target utilization. And then your online decision here is just the difference between the target and the current utilization value. And then as for the connection to the actual energy application of storage-assisted energy procurement, what you can do is as you are receiving online energy demand of D sub T, what you can do is initiate an instance of K-min search, and you just set K to be equal to the energy demand. And this is a technique introduced in in the existing work of this problem without predictions. So these threshold algorithms are pretty straightforward, easy to use, but somewhat difficult to design. In particular, for this version of the problem, you need to solve K balancing equations in order to minimize the cost ratio in each setting. And now we can move on to the learning augmented setting. So now how do we design this threshold once you have a prediction? And so for this particular simple problem, all you need is a prediction P for the minimum observed price of the time horizon. And this is because if you know the minimum price, then the optimal solution is just to save up all of your buying power for the moment that the price actually rises, and you incur a cost of K times P. But we want to modify this so that we can guarantee certain levels of robustness and consistency. And the way we do this is that the intuition here is thresholds that are slightly above the prediction P will most directly affect the consistency metric when the predicted value is close to the ground truth minimum. And so then in this setting, we solve the K balancing equations to guarantee a certain level of consistency. And then on the other hand, if you're for threshold prices that are far from the prediction, if the minimum price falls in these regions, then you're most likely in a setting of robustness where your prediction has been inaccurate relative to the ground truth. And so then we will solve these threshold prices to guarantee the level of robustness. And then as for the connection to the energy storage setting, we recall basically we just initiate DT min search, and then to make this learning augmented, it's very straightforward. We just apply this modified threshold-based algorithm, and we initiate the DT minimization learn augmented algorithm to solve the storage setting. So this is the background for why, in order to solve this storage-assisted energy procurement problem, solving for this foundational K-min search problem is necessary. And then just to give a brief overview of the theoretical results. So the first thing we consider is an intuitive naive baseline of learning augmented algorithm. So basically, if you have a prediction, you can have two different algorithms. You can have an algorithm that will basically ignore the prediction and generate a solution that is completely worst case optimized, or you can have an algorithm that is fully trusting the prediction and will directly solve the optimization problem based on the predicted values. And so what you can do is you can just split the portion of K resources between these two algorithms and then sum up the cost. And you can set this proportion between 0 and 1. And in this graph, we set K equal to 20. And if we use this naive baseline, we have a pretty graceful robustness consistency trade-off. In both settings, the robustness degrades from the optimal competitive ratio alpha to U over L, and the consistency also improves from alpha to 1. And your position on this curve will depend on how much you decide to trust this prediction based on a parameter lambda. And so the main takeaway here is that our optimal Pareto optimal algorithm has a pretty considerable improvement over this naive baseline, which indicates that carefully setting the threshold is necessary to have the best improvement. And also to verify the results, we have some experiments on real data traces. And so we tested for electricity prices. We took the prices from the real-time electricity market from 5 different ISOs in 2023. And there can be considerable variability from day to day. And then to model the demand of the power, we used a demand traces from Akamai in the corresponding locations, the 5 different ISOs. And then we assume that some portion of the demand can be met by renewable generation, which makes the corresponding net demand a bit more unpredictable. And I'll go through the results pretty quickly. So first, if you want to test for prediction quality, our algorithm we'll say is given a parameter lambda from 0 to 1, which dictates how much it's using the prediction. And this last curve is just setting lambda equal to 1. And as a prediction model, it's relatively simple. It just assumes the minimum price is the minimum of a sliding window, and then we add prediction error from a normal distribution. And so this prediction model is somewhat simple, but we choose it to demonstrate that our algorithm does not actually depend on the quality of predictions to have performance guarantees. And so the takeaway here is that you want to set lambda equal to 0 for accurate predictions. You also, but when the prediction errors are comparatively high, you want to use the worst case algorithm for inaccurate predictions. So it's kind of interesting because the best result, the lower envelope here is setting lambda equal to 0 to 1, but also setting lambda equal to 0, 1 is also somewhat close to the worst case upper envelope of this graph. And so you want to set lambda carefully for when you're using the learning augmented algorithm. And so I'm actually pretty close out of time, so I'm going to skip this. And so some future work, you can have prove some theoretical performance bounds for more realistic inventory dynamics. And our main contribution is that we show a learner augmented algorithm for general online search and apply it to storage assisted energy procurement. And thanks, and that's it for my talk.
Any questions? So, oh yeah, here's.
Thank you for your presentation. My question is that, is there any theoretical analysis on the impact of the prediction error on the robustness and the consistency of the algorithm you proposed?
Yes, so actually the robustness and consistency guarantees are close, basically equivalent to the trade-offs for the general K-min search setting. You just have to assume that the storage capacity is enough so that you can trade in each time slot. So yes, that's a good question. Yeah, for the storage setting, it matches the K-min search. Thanks.
Okay, sure. Thank you.
I guess it's a long session, so 2 hours, and now it's time for the break. And then thank you for being here. And then after the break, there will be a poster session in the hallway.